Hey everybody, in this video I'm going to explain to you how to do a chi-square test of independence and also a chi-square test of homogeneity, although that part is going to be a lot faster than the independence one because they are basically the same test. So let me share up the notes and we'll get started. So here we are at chi-square independence tests. So here's the idea. Here's what the basic premise of a chi-square independence test is. The basic premise is that we're going to take two different qualitative variables, each of which may have any number of categories. You can technically do this with as few as two categories, but usually you would want to do a two proportion z-test in that case. So usually three or more categories is where you're going to want to use this test. So I've got these two categories, age and gender and favorite ice cream type. And what we're going to do is we're going to see if those two things, those two variables are related or not, right? So that's why it's called an independence test. We're testing to see if those two variables are independent or if they are dependent, which is to say, if there is a relationship, they will be dependent. And if there's not a relationship between those variables, then they will be independent. So to do that, I need to explain a fair bit of stuff that we're going to do. Now, in actual practice, what we're going to do is we're going to type this chart into our calculator and hit a button, and it's going to tell us if they're related or not. But I really want to explain, well, what's going on essentially when you hit that button in your calculator, like what's it doing and why. So the way I need to explain that is we need to start with a contingency table. So if you remember, back in chapter 2, I believe it was, we learned about data display. When we were learning about data display, we learned about contingency tables. And here's what a contingency table is, right? I've got two variables, both qualitative in this case, favorite ice cream type, and age and gender category over here. So I've got women, men, girls, and boys for my categories, my age and gender categories, right? Adults and kids and male and female, all broken down into 4 categories. And then I've got favorite ice cream type, cup, cone, sundae, sandwich, and other. And so what this means is if we look at the totals, right, we surveyed 547 people about this triviality for some reason. And we found that like 51 of the girls preferred their, 51 of the people we surveyed were girls who liked their ice cream in sundae form. And 29 of the people we surveyed were men who liked their ice cream in cone form. And 11 of the people that we surveyed were women who like their ice cream in some other form that's not delineated here, right? So that's how you read this table. I think it's fairly clear, to be honest, but might as well go over it as long as we're going over everything. So I need to explain 2 concepts. One is the marginal distribution, which is simple. And then the other one is the conditional distribution, which is a little bit less simple. So marginal distribution is you take one row. So if I wanted to find the marginal distribution of the variable favorite ice cream type within this sample, it would be this. It would be just the fraction that fell into each category, or the percentage that fell into each category, right? So of the categories favorite ice cream type, cup, cone, sandwich, sundae, sandwich, and other, 107 out of the 547 people fell into the cup category, and 109 out of the 547 people fell into the cone category, etc. Right? And so the marginal distribution of favorite ice cream type is this right here. Do I have the whole piece? Yeah, is that right there? And that's it. That's all marginal distribution is. Notice that marginal distribution is exactly the same thing as relative frequency. Right? Literally no difference between marginal distribution and relative frequency. That's it. They're the same thing. So we could find the marginal distribution for age and gender above, and it would just be these things out of 547, right? So marginal distribution of women, 131 out of 547. Marginal distribution of men, 105, or not marginal distribution, excuse me. I'm saying it really badly. The marginal distribution of age and gender is women, 131 out of 547. Men, 105 out of 547. Girls, 141 out of 547. And boys, 170 out of 547. You can turn those all into percentages if you want to. It really doesn't make much difference. That's marginal distribution. It's just relative frequency. It's relative frequency of a particular category. Now, the slightly more complicated one is conditional distribution. So conditional distribution looks something like this. What you do is you fix one variable, and then you find the marginal distribution within a category of that variable. So I'm gonna fix age and gender, and then within each category of age and gender, I'm going to find the marginal distribution of favorite ice cream type. So I would read this as the conditional distribution of favorite ice cream type given age gender. Right? So conditional distribution of variable A given variable B, you pick a category of variable, well, you do all the categories of variable B, and then within that category, you find the marginal distribution. So the marginal distribution of favorite ice cream type given age gender means that I take one value of age gender and find the marginal distribution within that. So here's the thing. When I look at this, so when we're working on women here, that's the data I've got. I'm ignoring all of this stuff right here, all of that, paying no attention to it whatsoever. We are looking only at the category of women, which means that our total is only 131, not 547. It's just 131. So the marginal distribution, or the conditional distribution of favorite ice cream type given that our respondent was a woman, is 42 out of 131 for cup, 30 out of 131 for cone, 25 out of 131 for sundae, 23 out of 131 for sandwich, and 11 out of 131 for other. Now, you don't necessarily have to remember all that because I wrote it all down here, right? Then we just do that for all the categories. So there we go, there's the rest of them. I just did them all once. And that's it. That's the conditional distribution of favorite ice cream type given age and gender. Now, let me encourage you to make sure that you can do this. I asked for the conditional distribution of favorite ice cream type given age and gender. Down here in number 3, I ask you to find the conditional distribution of age and gender given favorite ice cream type. So what you do is you fix a value of favorite ice cream type like cup, and then you find all the proportions within that. So there'll be different distributions, but I just wanted you to know what you're finding there. So all that said, here's what we're going to do for a chi-square test of independence. Here's the idea. So I need to explain the basic idea here. So the basic idea goes like this. Our null hypothesis is going to be that the variables, in this case, age, gender, and favorite ice cream type, are independent. That is to say, one has no effect on the other one. The alternative hypothesis is that they are dependent. In other words, we are going to need to see significant evidence that the two are related for us to think that they're related. Our default is going to be they're unrelated, one has nothing to do with the other one. And then the alternative, if we see significant evidence of it, we will believe that the two of them are related, that there's some sort of correlation between age, gender, and favorite ice cream type. Here's how the math works. The null hypothesis is that they are independent, that one has no relationship to the other. So what that means is, so here's my table. What that means is, if it is the case that age, gender has no effect on favorite ice cream type, then we would expect the marginal distribution of women, marginal distribution of favorite ice cream type for women to be roughly the same as that for men, which is going to be roughly the same as that we would see for girls and for boys. In other words, that the various conditional distributions, or excuse me, the various marginal distributions for each category of age and gender should be about the same. That is to say, that they should all be about the same as the total. So in other words, here's the idea. We're expecting that the number 42 out of 131 should be about the same as the number 107 out of 547. Now, the way we calculate that, I explained it all in text down here. It might be a little bit easier to see. So if the variables are actually independent, then our best estimate of the proportion of all people who prefer their ice cream in cone form is this, 109 out of 547, right? So that's, oh my God, it's all over the place. Oh, we're doing cone. Okay, so my best estimate of the proportion of all people who prefer their ice cream in cone form is 109 out of 547. If we interviewed 131 women, well, since we interviewed 131 women, I would expect that the proportion of women who prefer their ice cream in cone form would be about 109 out of 547 times 131, right? The fraction that we are guessing our best estimate of the fraction that of the population in that category times the number of people in that category. Now notice, this is exactly the same as we did up here, where when I wanted to calculate the expectation, we had this percentage that we thought was going to be the percent in that category, and we multiply that percentage times the number in that category, or times the size of the population. Well, that's what we're doing here too. It's just that our percentage, instead of being given to us in just like a table where we say, 37% of Americans have blue eyes, well, we say, okay, for our purposes, we think that 109 out of 547 of everyone that's the fraction of everyone who prefers their ice cream in cone form. And so if I take that number, 109 out of 547, and multiply it by the number of people in the category for women, that's the number that I would expect to fall into this category. Now, the number we actually saw in here was 30. But our observation is 30, and then our expectation is 131 times 109 over 547. That's what you do. Now notice that I've got, 20 cells in here? So we could do this by hand, right? I could do 131 times 107 out of 547 for our expected value for cup, and then our observed value for cup is 42. Now I could do observed minus expected squared divided by expected, get a chi-square contribution from this cell. Then I could do the same exact thing for cone, and for sundae, and for sandwich, and for other for women. And then I would do the same thing for men, cup, cone, sundae, sandwich, other. As you can imagine, this gets tedious. We're not going to do it by hand. Here's what we're going to do instead. Your calculator has a very, very nice, essentially one button thing. Well, not one button, you have to type the table in, but once you type the table in, it essentially has one button for you, which is really convenient. One button that does the whole thing, which is really convenient. So we're gonna go do that. That's what we're gonna use. So here's the idea. Let me explain the hypotheses, I guess, and the degrees of freedom. Degrees of freedom are slightly different in this case. Now, remember in goodness of fit, it was just categories minus one. Well, we have categories in two different variables. So just as a very, very brief description of what a degree of freedom is. A degree of freedom is essentially one way in which the data can vary. I know that's very vague. What it means is, if we know the totals, like if I know there's 107 people in this first category, or in the category cup, and I know 3 of the values, or 3, then I can find the fourth one is fixed. So once I have these 3, this one can no longer vary. So what that means is I get 3 from here and 3 from, and you can make the same argument going sideways, by the way. So like if I know the total and I know the first 4 of the sums, or first 4 of the data values, then the 5th one is fixed and cannot vary. So what that means is that I get -1 from each of the number of categories. So rows -1 times columns -1. Then I multiply them together, because all of these, like if I were to know all of these things, these 12 right here, as well as the totals, as well as all these totals, all the rest of this stuff has to be fixed. So that's what degrees of freedom are. So what that means is that we've got rows minus 1 times columns minus 1. So so this is columns, right? So I have 5 columns. I'm going to use 4 because that's columns minus 1. I have 4 rows. So I'm going to use 3. That's rows minus 1. And so my number of degrees of freedom in this case is 12. We'll see that when we do the test in just a second. So that's how you calculate degrees of freedom here. I've got it all written down here if you want to look that up in the notes. It's all right here. Yeah, rows minus 1 times columns minus 1, where R and C are the number of rows and columns. And that explanation I gave you, I didn't actually write it in here. You don't really need to know it. What a degree of freedom is actually kind of beyond the level of this class, but there you go. It really is a way in which your data can vary, essentially. It's one dimension. If you're doing this in terms of multi-dimensional analysis, it is one dimension. A degree of freedom is a dimension, essentially, like length or width. Okay, that was a bit of an aside. So here's what we've got. Our null hypothesis and alternative hypothesis are always the same for every independence hypothesis test. The variables are independent, variables are dependent. You should never write the variables. Notice I put them in brackets to emphasize that's just my example. Don't do it like that. Do it instead like this. Right? If you were, where'd my mouse pointer go? There it is. If you're doing a, whoa, what the heck happened there? Sorry, computer is freaking out on me. If you're doing a hypothesis test about whether ethnicity and political preference were independent or dependent, right? Ethnicity would have several categories, political preference might have several categories. So your null hypothesis would be those two variables are independent, and the alternative hypothesis would be they are dependent. Similarly, if you think that maybe women and men tend to drive different colored cars, right? Like men, maybe you're thinking that men tend to drive flashier cars and will have a lot more like reds and greens and weird nonsense colors, and that women will have boring car color choices of like tan and silver and all that, right? You could do a hypothesis test about that, and so you would have gender and car color, your two variables, are independent. It's your null hypothesis, and dependent is your alternative hypothesis. So good null and alternative hypotheses look like this, not like this, but this is just like the generic version. Okay, so we need to do all of the normal stuff for finding our p-value and determining whether we're supporting the null hypothesis or the alternative hypothesis. But first, let's write down what our hypotheses are. Let me get a whiteboard going here. So we're going to have a null hypothesis of toolbars in the way. So my null hypothesis, my two variables were age, gender, and favorite ice cream type, and favorite ice cream type. Just move this out of the way. Are independent. That would be my null, and my alternative hypothesis, of course, is that they are dependent. I'm just going to say they, which is a little lazy, but that's okay. It's clear enough what we mean. They are dependent. Okay, so the way we're going to calculate this p-value and make our determination from there about which hypothesis we're going to support is not going to be by hand. It is a hassle to do these by hand. I don't remember if I've ever done one of these by hand. I feel like I've done some, but not very many. So I'm going to go back to the notes, and we're going to explain how to do this all in your calculator. So here is how you do this type of test on your calculator. So the first thing you need to know is what a matrix is, because that's how your calculator interprets a table. So a matrix, for our purposes, is basically just a block of numbers, right? Looks something like this. This matrix is 3 by 5. It is 3 rows by 5 columns. It's always rows by columns. So this is a 3 by 5 matrix. That size is going to be important because you're going to have to tell your calculator how big your matrices are. And what we're going to do is we're going to put this table right here, into a matrix. So this part of the table, not the totals. Don't put the totals in. So we're going to put this part of the table into a matrix in our calculator. So let's see how we do that. Calculator, matrix. For me, the matrix button is right here. Some of the older versions actually just have a button labeled matrix, so it may be in a different spot for you. It's going to be somewhere in this general vicinity anyway, but for me, it is this second function of x inverse. And we get these three categories of names, math, and edit. Now, we're not going to do anything with math. If you get more into matrices, it turns out they are super interesting. We're not going to do any of the interesting stuff with them. We are just going to use them as tables. So names, this is where if you want to, like, so here, I'll show you what happens. If I hit enter on this, it's just going to give me A in brackets like that. This is how you tell the calculator use matrix A. What we want to do, though, is we want to edit a matrix. So we're going to go over to edit. And then we're going to select which one. I'm going to select matrix A. You can select whichever one you want. I would recommend doing A. I'll show you why when we get a little bit further on, but I'm going to do A here. So if you remember, our matrix was 4 by 5. I've got 4 categories for age, gender, and 5 for favorite ice cream type. So the number of rows is 4, number of columns is 5. You have to type that in first, so your calculator will make you the right size matrix here. Excuse me, my portrait. And then all I'm going to do is I'm just going to type in the table. 42, 30, 23, 11, 31, 29, 15, 23, 7, 23, 51, 42, 6, 15, 27, 60, 54, and 14. Let's make sure I did that correctly. 11. Oh, and by the way, I'm hitting the enter key each time to move to the next entry. You can also use the arrow keys to move around. So arrow keys will move around. If I hit enter right here, it'll just move me one to the right. And then when I get to the end of the row, it'll move me to the next row like that. So I was just hitting enter to move from one to the next. All right, so 42, 30, 25, 23, 11, 31, 29, 15, 23, 7, 19, 23, 51, 42, 6, and 15, 27, 60, 54, 14. Okay, by some miracle, I've made no errors, which is very unusual. So I'm going to quit out of here. And then here's where we're going to go to do this test. It's actually very, very convenient. So I'm going to go to stat and tests. Stat, tests, and all the way to the bottom, Chi-square test. Notice there's Chi-square GOF test. If you want to do a goodness of fit test in your calculator, you can. They're not that hard to do by hand, to be honest. I'll show you how to do that one. Maybe, I should have showed you in the goodness of fit video. I'm not going to ask for one in the calculator because not all of the versions of the TI calculators have this, and I've seen other calculators not have this test. So if I ask for it on a test, I'll ask you to do one. I'll ask you to do it by hand, right? And by hand is what I mean is like what I did in the goodness of fit video, where of course, right, I write it all out, but I don't actually do the calculations by hand. I type those in the calculator. But that's what I'll ask for on a test. So maybe don't worry if you do have this. Don't even worry about it. We're not going to use it because not everybody has it, and it wouldn't be fair. So we're just going to use chi-square test. So when they say chi-square test, this is for both independence and the one we're going to talk about in a little bit, homogeneity. A lot of books and teachers just call this a chi-square test of association because they're the same test essentially. The only difference in them is how you write the hypotheses. So chi-square test. Now, it's going to ask us for two things, sort of. It actually only asks us for one. It's asking us two questions here. I know it doesn't look like it, but what the calculator is asking is, where did you put the observed values, and where would you like me to put the expected values? So the calculator is going to calculate all the expected values for us in the same way that I described earlier. It's going to do, row total times column total over overall total. For all of the cells, and it's just going to put those into a matrix, and then it's going to do observed minus expected squared over expected for each of the cells in the matrix. So we don't have to calculate the expected values. It's going to do all that for us. So the only thing we really have to fill in here is where we put the observed values and where we would like the calculator to put the expected values. So the default is observed and expected to be. So I'm just going to leave it like that and go to calculate. And it spits out a p-value for us, right? Gives us our chi-square test statistic of, in this case, 61.6 or thereabouts, and a p-value of 1.15 times 10 to the -8. So very, very small. And notice that it has 12 degrees of freedom, just like we said it would, right? Rows -1 is 3, columns -1 is 4, 3 times 4 is 12. That's how we do it. So our chi-square test here is 1.15 times 10 to the -8. So here's how I would want you to write that on a test, something like this. There's my whiteboard. So chi-square test. Chi-square test. Chi-square approximately equal to 61.6. P-value about equal to 1.15 times 10 to the -8. Less than 5%. So reject. H0. Right, something like that. This is what I would be looking for on an exam question or a quiz question or anything like that. Now, we can certainly draw a picture if we would like. It's going to look basically like this, right? So chi-square with 12 degrees of freedom. It doesn't actually look exactly the same. It's a lot more stretched out than the one that we had with 3 degrees of freedom from goodness of fit, but the basic shape is the same. Right, so you'd have like here's 12, and then we'd have 61.6 way over here, 61.6, and then that area is your p-value. Right, so you could do it with chi-square CDF if you wanted to. In fact, I might as well. Right, I'll do chi-square CDF of 61.6 up to infinity with 12 degrees of freedom, and we'll see that we get pretty much the same thing that we got doing it the other way. Right, so 1.15 times 10 to the -8. It's going to be a little bit different because I'm rounding off, obviously, but basically the same. So if we were to do this, chi-square CDF is 8, 61.6 up to infinity with 12 degrees of freedom. And lo and behold, 1.15 times 10 to the -8, just like we thought. So as you can see, same thing. That's what your calculator's doing. One thing I do want to point out is this. If I go back to the matrices and I go look at matrix B, you can see that it put all the expected values in there, right? We didn't have to calculate those at all. It calculated them for us, which was really nice, right? Very convenient. But yeah, we don't actually really have to concern ourselves with this. One thing that you can do if you're doing kind of a more in-depth analysis is you can try and figure out where the expectations and the observations differed by a lot. And so you can zoom in on which categories were very different than we thought they were going to be and which ones were basically the same. So for instance, we can see that women and cup, right, 25.625 was the expectation. And if we go back and look at the notes here, we can see that women and cup, the observed value was 42. So that's actually quite different, right? 42 is a lot different than 25.6 when your expected is 25.6. Right, so you'd end up with a pretty big contribution to the chi-square overall, and you can go compare them one at a time if you want to. I'm not going to worry about that. That's not a thing that we're going to zoom in on. I just want to do the sort of broad strokes of the test. And if you ever get farther into this, like in a future stats class, that's the thing that you'll concentrate on a little bit more. All right, let's go back to the whiteboard, and I don't think we have too much more to say. Let's look at our null and alternative hypotheses, right? So null hypothesis was age, gender, and favorite ice cream type are independent, and the alternative was they're dependent. We think that there is enough information here to reject the null hypothesis, so we think that they are not independent, but instead that they are dependent. So that's what my conclusion will be. Pardon me, my computer is telling me that my latest video is done encoding, and it won't let me click until, hello? Can we stop now? Well, let me click a new window until I tell it to stop. So, conclusion. This data suggests that a person's preferred ice cream type depends on their age and or gender. You could definitely write that in a much more generic way. You could say, this data suggests that preferred ice cream or favorite ice cream type and age gender are dependent variables. Totally fine. That's a perfectly legitimate conclusion. I'm trying to make it a little bit more colloquial, more understandable by the layperson, basically. But that other one that I said, totally fine. If you write that on a test, full credit. That's basically it. That's how you do a independence hypothesis test. So I want to talk about homogeneity hypothesis tests as well, and we'll see that they're the same, basically. I'm going to come back to this one. I have a couple of sort of bonusy questions here at the bottom. So normally, like I said, this lecture would be in class, and we would do these things, put everybody in groups, let them figure out how to do this. I'm going to come back to that in a little bit. For right now, what I want to do is talk about homogeneity tests and why they're just exactly the same thing. So homogeneity test is asking, if I have a bunch of categories, okay, so let me back up a second. I didn't say that very well. They're called homogeneity because what you're asking about is, do these different populations have the same distribution of this one variable? So in other words, you could ask this in a homogeneity test way by saying, do the different populations, women, men, girls, and boys, have the same distribution of favorite ice cream type? In other words, are those distributions homogeneous across populations? That's why it's called a homogeneity test. The only effective difference here for what we're going to do is how you write the hypotheses. In actual practice, you might want to, if you're thinking of, say, this category and this category, not as categories, but as actually different populations, it might mean that you go about gathering your data a little bit differently, but that's about it. For our purposes, since we're not actually gathering any data, it means that the difference between the two is just literally just semantic. So if you remember, what we did was we were comparing whether the marginal distribution within each category of age gender was the same, or was similar enough for us to think that they all came from the same population. Or excuse me, was similar enough for us to think that all of the marginal distributions were relatively close to each other, and so that would tell us that the variables were independent. What we're doing in this case is we're thinking of, we've got two entirely different populations here. And so we're going to check to see if the marginal distribution of this variable within each of those categories, or within each of those populations, is the same. And if it is, it makes us think that the two are really from the same population, right? That's what our test is about, is, are these two populations really the same population? So the way we write that is something like this, right? So I'm going to do this with drunk driving. I don't know why I have this juxtaposition of like ice cream and drunk driving fatalities. Those seem very, very different, but that's what we're doing. So I've got these two different categories of accidents, right, that I'm thinking of as different populations. That is to say, accidents that involve alcohol and accidents that don't involve alcohol. And so we're rating the severity of injuries in the following way: no injuries, minor injuries, severe injuries, or one or more fatalities. And we want to know, so essentially we already know that alcohol causes more accidents. Now what we want to ask is, are those accidents more severe? Like, is the severity of accidents different in those involving alcohol and those not involving alcohol? And so we get a sample of accidents that involve alcohol. We get a sample of accidents that don't involve alcohol. And we test to see if their distribution of severity of injuries is the same or not. And mathematically, that's exactly what we were doing before, right? It's the same thing. So it's literally the same test, right? There's actually no difference in the math, right? You're sort of thinking of them differently, but there's no effective operational difference. You're going to do literally the same exact thing. So the way we do this is precisely the same. I'm going to make a 2x4 matrix and do exactly the same thing we just did. So let's do that. Let's go write some hypotheses. I might as well not be careless about this. We'll write some hypotheses. Here they are. Right, those are the hypotheses, and then we will just jam all that into our calculator. So since I've got them typed out here and you have them in the notes, I'm just going to leave them here and not write them on the whiteboard. But I'll share up a whiteboard and we'll do this. Let's make another page. So we're going to do a chi-square test. Chi-square test. So let's go to the calculator. I need to go back here first and then go over to the calculator so that I can see them both, so I can see the table to type it in. So I'm still looking at matrix B here. I'm going to quit out of this. So what I'm going to do is, instead of deleting my old data for matrix, I'm going to go to matrix C, and I'll show you how to change the matrices from the default settings in the test. So we're going to go to C. Oop, gosh darn it, I do that all the time. So they have the names as the first category, and edit, which is where I go most of the time, as the third one, which is always a little annoying. So this is going to be 2x4. It's 2x4 because I've got 2 rows and 4 columns in my matrix. And so we've got 38, 58, 87, 19, 105, 107, 81, 24. 24. Yeah. Oh, no, I didn't get that one right. This is 87, not 57. Always got to check my matrix just to make sure it's right. I get so many typos in here. So we're going to quit out of that. Then I'm going to go to stat tests, chi-square test. My observed now are in C, so the way I change this A to a C, you can't just like put in bracket A, close bracket. It doesn't understand that. What you have to do is you have to go to matrix and select the name C. And similarly, so if I do B, I can do B here, but I'm not going to, because it'll delete everything that's in B, right? And so I might want to return to that later, so I'm going to change this one to D. Calculate it up. There we go. So yeah, this is some pretty strong evidence. P-value 5.5 times 10 to the negative 5. This is some pretty strong evidence that we're going to be rejecting the null hypothesis. That is to say, let's flip back and see what that says. That is to say that we think that there is a difference in severity of injuries, right? We think that the null hypothesis is not correct, and instead we think the alternative is correct. Distribution of severity of injuries in a traffic accident differs depending on whether alcohol is involved or not. Right? And you can see we got those things. I've typed them out, wrote them out before. Chi-square of 22.35 and a p-value of 5.5 times 10 to the negative 5, which is the same thing as 0.000055. Significantly smaller than 5%. So my conclusion is this. It's literally that. Distribution of severity of injuries differs depending on whether alcohol is involved or not. And if we looked a little bit further into it, right, we don't have to look much further, but if we looked a little bit further into it, we can see that when alcohol is involved, we get significantly fewer non-end minors and significantly more severe end fatalities than we would get with alcohol. And you might say to yourself, well, wait a minute, 87 doesn't seem much bigger than 81, and 19 is actually smaller than 24, but keep in mind that our population of alcohol-related accidents is much smaller than the population of non-alcohol-related accidents. So we would expect, since this number is only about 2/3 of that one, we would expect this number to be 2/3 of that one, and this number to be 2/3 of that one, if they were to maintain the same ratio, which they're not, right? These are bigger than 2/3 of, like the 19 is 3/4 of 24, about 79%, something like that. And 87 is actually bigger than 81 when we would expect it to be smaller since it has a smaller population. So yeah, this is enough evidence for us to suggest that severity of injuries is increased in accidents involving alcohol, which makes sense, right? If drivers are impaired, they might slam into each other at higher speed than if they are not impaired, causing more injuries. Okay, so that's how that works. I've got one for you guys to try down here. Feel free to work on that. Very straightforward, right? You're just gonna jam this into jam that into a matrix and see what the answer is. I will go up here. Actually, I might leave these for you. So for number 4, we answered that one. We do think the favorite ice cream type depends on age and gender. This one, I want to leave that one for you to think about, which is the way we would do it in class. I want to know if favorite ice cream type depends on age, or if it depends on gender, or both, right? Because we said that we think that favorite ice cream type does depend on age/gender, but which one is it? Is it the ages? Does it depend on age? Does it depend on gender? Does it depend on both? Which one? So what you can do to use your existing data to find out, and I will leave you to that, is you can combine. You can do like kids and adults, right? You can do a table for kids and a table for adults. And what you do is the table for adults is the sum of these two, right? The women and men categories. So you'd have the first entry would be 73, then 59, then 40, then 46, then 18. And then for the kids, you do this: 34, then 50, then 111, then 96, then 20. And I will spoil it for you here a little bit. So don't listen if you don't want spoilers to how this exciting test comes out. I'll pause for a second. Okay, now that all the people who don't want spoilers are gone, it turns out that according to this data, it will depend on age and not on gender. So in other words, the kids like different kinds of ice cream than the adults do, but the males and females exhibit no particular correspondence between. There's no particular relationship between gender and favorite ice cream type. So if you actually do those tests, those are the answers you should get. Okay. I think that is all I wanted to say about these things. Yes. Yes, that's all I want to say about independence and homogeneity. I know it's been kind of a long video. That's always the bulk of this lecture. But I will leave it there for independence and homogeneity. I'm going to go ahead and stop the video now, and in the next video, I'll explain an entirely different kind of chi-square test that is not. It's a quantitative test that uses a chi-square distribution, but everything's calculated in a totally different way. So it's a test of a single variance, and I'll explain that in the next video. All right. So I will see you in the next video then.